Hello, my name is Levi, and today I'm going to talk about approximately counting and sampling Hamiltonian motifs in sublinear time. This is a joint work with Talia Eden, Dan Aron, and Rubinfeld. Some of the slides that I'm going to use are taken from Talia's talk, and some of the terminology that I'm going to use doesn't appear in the paper, but I will use it to avoid getting into too many technical details. So what are motifs? Motifs are recurrent and statistically significant subgraphs of a network. Counting motifs has many applications in many research fields such as biology, chemistry, and social network sciences. In the problem of approximately counting motifs, the input is a query access to a graph G and an arbitrary motif H. And the output is the number of different copies of H in G, where a copy of H in G is a subgraph of G, which is isomorphic to H. So in this slide, you can see that we have a large graph G and a small motif H, and we have at least three different copies of H in G. We also address the related problem of sampling almost uniformly a copy of H. In this problem, the input is again query access to a graph G and an arbitrary motif H, and the output is a uniformly distributed copy of H in G. So each time we ask for a sample, we get a uniformly distributed copy of H in G. And each copy of H in G should be sampled with probability, which is roughly 1 over the number of copies of H in G. This problem also has many motivations in various research fields. The regime that we are interested in is the sublinear query complexity regime, where we access the graph through queries, and our motivation is to obtain a number of query complexity which is sublinear. We consider two query models. The first model is the general query model, in which we allowed to make three types of queries. The first type of queries is the degree queries, where we are indicating a vertex, and the return value is the degree of the vertex. A neighbor query, where we are indicating a pair which is a vertex and an index J, and the return value is the jth neighbor of V, the vertex we indicated. And pair queries, where we are indicating a pair of vertices, and the return value is whether there is an edge between these vertices or not. In the more recent augmented model, we are also allowed to have uniform edge queries, in which we get uniformly distributed edge in the graph. And this model was shown to be strictly more powerful than the standard model, the general query models that I will refer to as the standard model from this point. So while in the augmented model, it's possible to count arbitrary motifs in sublinear time, in the standard model, it was shown that it is possible to count motifs which are edges, stars, triangles, and cliques in sublinear time. And in this work, we extend the family of motifs that can be counted in sublinear time. We extend it to be every motif which is Hamiltonian, namely any motif that has an Hamiltonian cycle in it. Before we describe our algorithm, let's first describe the algorithm in the augmented model that counts by almost uniform sampling copies. So in this example, we are now allowed to access uniform edge samples, and let's consider for this slide even length cycles of length k. So a simple algorithm goes as follows. So we have a sampler that attempts to sample a copy of a k cycle from the graph. By performing the following steps, it first samples k over 2 edges from the graph uniformly at random by performing random edge queries, and then it performs k over 2 pair queries to check if a cycle is formed. And if so, it returns it. So this algorithm attempts to sample a copy of a cycle from the graph uniformly at random. So let's see how it goes. So if I consider a specific copy, what is the probability that this sampler would return this copy? So for each one of these, so if the copy is a cycle of length 6, then each edge, each alternating edge in the copy is sampled with a probability 1 over m by the first step of the algorithm, and then therefore we reveal the specific copy with a probability which is roughly 1 over m cubed. So how can we make this attempt to sample a copy into an algorithm that approximately count the number of copies in the graph? So let's consider a specific copy of a cycle of length 6 in the graph. As we saw, the probability to sample this specific copy is roughly 1 over m cubed. Sorry. And now, what is the probability that some copy is returned by the sampler? The probability to return some copy is equals the number of copies over m cubed. Therefore, it suffices to repeat the above sampler, roughly m cubed over the number of copies, many times to get a multiplicative estimate of C6. This is up to polynomial factors in 1 over epsilon, which is our proximity parameter. Therefore, for general event cycles of length k, the number of queries that are sufficient in the augmented model is m to the power of k over 2 over the number of copies. Please note that a copy may be returned with probability which is slightly greater than 1 over m cubed. However, this doesn't affect the asymptotic complexity of the problem. Also note that we need to have some kind of a constant factor approximation guess on the number of copies. Here we can use a search scheme such as appears at Eden et al. And actually this upper bound is tight for odd cycles and clicks, as there is a lower bound of omega of m to the power of k over 2 over the number of copies. Many queries for odd cycles and clicks, one that appears at Asadi et al. And one that appears at Eden and Rosenbaum. Both lower bounds reduce the problem to the problem of set disjointness. So reduce from the problem of set disjointness. Okay, so let's go back to the standard model. In the standard model, we have an additional lower bound that goes by a heating argument. So the heating argument, the lower bound is omega of n over the number of copies to the power of 1 over k. And the lower bound it goes as follows. It argues that we cannot distinguish the empty graph from a graph that has a clique of side ck to the power of 1 over k. And therefore, we cannot approximately count the number of k cycles unless we take this many queries, because if we don't take this many queries, we don't have a chance to hit the clique. And now let's consider a special case in which we have copies of cycles, and all these cycles have a special configuration. And from now on, I will focus on cycles, but all the algorithms that I will describe also applies to any Hamiltonian motif. So the first special case that we are going to consider is the case in which all the vertices in the copy have low degree. Specifically, we set the threshold to be ck to the power 1 over k, and we denote this by gamma. So we say that a vertex is gamma low if its degree is at most gamma. And now we consider sampling copies in which all the vertices are gamma low, and we would like to match the same bound as the low bound from the previous slide, namely omega of we want to make a number of queries which is O of n over ck to the power 1 over k. So we are going to try to attempt to sample a low degree copy as follows. We first sample a vertex in the graph uniformly at random, and then we proceed in k minus 1 iterations by performing some uniform random walk of k minus 1 steps. More precisely, in each iteration, we consider the current vertex. So initially, the current vertex is V1, the vertex that we uniformly sampled from the graph. And then we check if the degree of the current vertex Vi is at most gamma. If it's greater than gamma, then the sampler fails. Otherwise, we pick an index j uniformly at random from 1 through gamma, and we perform a neighbor query on the pair Vij. If the neighbor query returns a vertex, which we denote by Vi plus 1, which is also gamma light, then we proceed to the next iteration. And finally, after making k minus 1 such steps, we perform a pair query between the first vertex V1 and the last vertex on the path Vk to see if the path closes a cycle with V1. So now let's see what is the probability to sample a specific copy, which is a low copy from the graph. The probability is to hit this vertex, which happens with probability 1 over n, and then to guess correctly each one of the indices along the path. Each index is guessed correctly with probability 1 over gamma. So overall, the probability to sample a specific copy C is 1 over n times gamma to the power of k minus 1, where gamma equals c to the power of k, ck to the power of 1 over k. Therefore, the overall success probability of this sampler to sample a copy is the number of copies over n times gamma to the power of k minus 1. Hence, if we make n times gamma to the power of k minus 1 over the number of such copies, many attempts, then we are able to successfully approximate the number of copies of this type. Okay, so this gives a tight algorithm for the case that we have vertices which are for the case that the copies consists of only gamma low vertices. Now let's see what happens if we have high degree vertices. So in the standard model, we are not allowed to sample edges uniformly at random, but we can partially simulate it. By performing a pre-processing step of cost O tilde of n over t, we are able to sample vertices u such that the degree of u is at least t with probability which is proportional to the degree of u. We refer to vertices of degree greater than t as t high vertices. So how can we sample edges incident to t high vertices almost uniformly? We will sample a vertex u with probability which is roughly du over 2 times the number of edges, m, and then return an edge incident to u uniformly at random. So how can we sample edges almost uniformly for high degree vertices? This is by a degree typical set. So a degree typical set is constructed as follows. We first pick a multiset of S vertices where each vertex is drawn uniformly at random from the graph and independently. Then we perform a degree query on each vertex in the sample. We denote by ES the edges incident to the vertices in S where we allow repetition since some vertices may appear more than once in the sample. Then to sample a vertex with probability which is proportional to its degree, we perform the following steps. We first sample V from our set S with probability which is dV over ES, namely with probability which is proportional to its degree. Then given V, we return a neighbor of V uniformly at random. Now let's consider what is the probability to sample a vertex U according to this process. So the probability to sample a vertex U equals the size of the intersection of the neighborhood of U with the multiset S over the total number of edges which are incident to the set S. On expectation, the size of the intersection of the neighborhood of U with the set S equals the degree of U over n times the size of S. And the expected size of ES is the average degree times the size of S. Therefore, the expectation sample the expectation of the probability to sample a vertex U equals the degree of U over 2 times the number of edges in the graph. Also note that if the size of S is at least O tilde of n over t, then the expectation of this probability, then the probability to sample U is concentrated around the expectation. Therefore, if the size of S is at least n over 2, then we call it a degree T typical set. Because it samples vertices with probability roughly du over 2m, as long as the degree of the vertex u is at least t. So if we have S which is a degree typical t, which is degree t typical, then we can sample edges incidence to T-high vertices almost uniformly. We first sample U with probability which is proportional to its degree, and then return an edge which is incident to U uniformly at random. As we can see here, we first pick an edge, a random edge which is incident to one of the vertices in the typical set, and then this allows us to sample U, and then from U we take a random neighbor, and this allows us to sample a uniform edge which is incident to vertices with degree at least T. Now, to see how we can use this tool, let's first define the notion of a configuration of a copy. So for a specific threshold T that will be determined later, the configuration of a copy is the classification of its vertices into T low and T high vertices. So previously we considered the configuration in which all the vertices were gamma low. Now we are going to consider a different configuration, which we refer to as non-adjacent high configuration. So we call a configuration non-adjacent T-high if all its T-high vertices, so if all the T-high vertices in the copy are not adjacent to each other within the copy. So for example, here we have a copy of a cycle, and as you can see, all the vertices that we classify as high are not adjacent to each other, and therefore this configuration is non-adjacent high. So if we set the threshold T to be at most a square root of m, then we can show that non-adjacent T-high copies can be sampled with equal complexity, which is roughly n over t plus m to the power of k over 2 over the number of copies. So how this procedure goes, and observe that by the lower bound that we have, we can tolerate t to be small as gamma. So how can we sample a copy of non-adjacent high configuration? So let's denote the number of high vertices in the copy in the specific configuration by L. So the configuration is the configuration determines the vertices which are high and the vertices which are low and their location in the copy. So in this case, we assume that we have L high degree vertices, and then that we know the location of each one of the high vertices in the copy. Then the procedure for sampling such copies proceeds as follows. We set T to be square root of m, and then we construct a degree T typical set of size n over T. So we can support a random edge sampling for vertices of degree at least T, namely for T-high vertices. Then we sample edges via the degree typical set, and if all the edges are of the form high-low, where high refers to T-high and low refers to T-low, then we attempt to sample a cycle with extending each one of the sample edges to a path by performing a random walk in which in each step we guess an index between 1 and t. We call this random walk t steps, and then to connect the paths we use pair queries. And if the edge samples along with the neighbor queries along with the pair queries form a cycle, then we return a copy. Okay, so the complexity, the probability to sample a specific copy according to this procedure will be 1 over m for each one of the L edges, therefore 1 over m to the power of n, and then the probability to guess correctly each one of the indices of the random walks would be 1 over square root of m, because the degree is bounded by t and t is square root of m. So the total probability to sample a specific copy would be roughly 1 over m to the power of k over 2. And therefore we are able to approximately count the number of copies that have non-adjacent high configurations. Okay, so now let's consider the case in which the copies have high degree vertices which are adjacent. The degree T typical set also supports sampling a vertex with probability which is roughly 1 over square root of m, as long as its degree is at least square root of m. How we do this? We first sample a vertex v with probability dv over the number of edges, and then keep it with probability square root of m over the degree of v. Since the degree of v is at least square root of m, then this is possible. So if the degree is smaller than square root of m, then this won't work. Okay, so how we can incorporate this to support sampling copies of adjacent high configurations? So let's consider, for example, this copy here, that in which we can partition the vertices into the vertices on the cycle into paths. So the first path is this path that we will try to catch via a single edge sample, and then 2 steps of two random walk of t steps, namely steps in which we guess an index between 1 and t. And for this single vertex, high degree vertex here, we are just going to use the ability to uniformly sample a vertex which is t high with probability which is 1 over square root of m. So the probability to hit this specific copy would be 1 over m times 1 over m to correctly sample these edges. And then we will also multiply this by 1 over square root of m, 1 for this edge, 1 for this edge, and 1 for this edge. And then also multiply by 1 over square root of m for hitting this vertex. So overall, the probability to sample a specific copy in this case is also m to the power of k over 2. So what are the hard configurations that we have so far? The hard configurations are configurations in which all vertices are not square root of m high, and not all vertices on the copy are gamma low. So this means that all the degrees in the copies are between gamma and square root of m. We refer to these vertices as medium. So now we have 2 thresholds. The first threshold is gamma, which equals ck to the power of 1 over k and square root of m, and the vertices that have degree in between these thresholds are called medium. The benefit of medium vertices that they enjoy the best of both worlds. Namely, if we set the threshold of the degree typical set to be gamma instead of square root of m, namely that it supports sampling edges uniformly from vertices of degree at least gamma, then we can sample edges incident to medium vertices almost uniformly. we can according to the query complexity, we are allowed to do so. We are allowed to reduce the threshold to be gamma, since this means that the size of the degree typical set would be roughly n over gamma. And then the other benefit of medium vertices is that they can also serve as a low degree vertex. Namely, we can perform a random square root of m step from a medium vertex, since the degree of the vertex of the medium vertex is bounded by square root of m. So let's put everything together. So first note that we can't sample a medium vertex with probability 1 over square root of m, which was the case for high degree vertices. However, we don't have to, because either all the vertices in the copy are gamma low, in which case we can sample such copies with probability which is roughly n over gamma, or the other case is that at least one vertex in the copy is a square root of m high vertex, in which case we can sample such copies by performing either the algorithm for non-adjacent or adjacent high degree configuration. So what we are left with are copies in which all vertices are either gamma low or medium, and at least one of the vertices is a medium vertex, otherwise we would be in this case. We can cover such cycles with a path of length, at least 2, that starts with a medium vertex. So this is helpful because we can first sample this edge here, and then we can continue extending the path by performing random walk steps, in which in each step we guess an index between 1 and square root of m. And finally, we perform a single pair query to see if this path closes a cycle with the initial starting vertex. So in this presentation, obviously there are many missing details. One thing that I didn't talk about is how we incorporate all these different configuration into a single algorithm that approximately count the total number of copies and not necessarily of a specific configuration. And in particular, we should take into account that not all copies are sampled with the same probability. We also need to obtain a constant factor approximation on the number of copies in order for this approach to work, and many other details that appear in the paper. So to summarize, what we did is to separately sample low copies, namely copies in which the degree of each of the vertices was bounded by gamma, where gamma equals the number of copies to the power of 1 over k. We sample such copies with probability which is roughly 1 over n times gamma to the power of k minus 1, and mixed copies which we sampled with probability which is roughly 1 over m to the power of k over 2. So overall, we obtain a query complexity which is n over gamma plus m to the power of k over 2 over the number of copies, which is tight for odd cycles. In particular, we also match the augmented the complexity in the augmented model up to a necessary additive overhead that emerges in the standard model. So now let's go over some open questions. One question is, is it possible to improve the upper bound in the both in the standard and the augmented model for some motifs. So the upper bound of m to the power k over 2 over the number of copies is tight for odd cycles and cliques, but it is not necessarily tight for all motifs. So an important question is whether we can improve it even in the augmented model. Specifically, what is the right complexity for counting the number of C4s in the graph. And another question that we leave open is the problem of counting motifs which are non-Hamiltonian. In particular, let's even consider simple motifs as paths. What is the complexity of sampling such motifs? Can we do it in sublinear with sublinear query complexity? And that's it. Thank you for listening.